So in 3.3 here, we're going to continue talking about these positions, the quantum numbers of these electrons, and so we're going to kind of, the big takeaway there, we're describing those, the traits of the 4 quantum numbers, okay, that we're going to be looking at down there. Okay. Oh, look, here's somewhat of a list of those. We have Planck's constant, particle masses, particle velocities, which is different than frequency, okay, momentums, and the Broglie wavelengths. Okay. This is just showing up again, n equals 1, 2, 3. That's just talking about those periods, the energy levels, the principal energy levels with it. So wave duality. Once again, don't worry about those. We don't need it. Schrodinger's equation for what we're going to look at. Okay, so electrons and atoms can exist only in discrete energy levels, but not between them. The energy of an electron in an atom is quantized, like we've been talking about. The energy can be equal only to certain specific values and can jump from one energy level to another. But it can't stay where it jumps to. It needs to relax always to its ground state. Now, the energy levels are labeled with n values, right? N equals 1, 2, 3, 4, 5, 6, all the way up to 7. We don't have any energy levels on the periodic table past 7, so we don't need to worry about energy levels 8 or higher, okay? So generally speaking, the energy of an electron in an atom is greater for larger values of n. So the energy of 2 is higher than the energy of 1, okay? So this is the principal quantum number or shell number, like we're talking about the shell. N equals 1, n equals 2, n equals 3. And different shells have different sub-energy levels, which we'll describe as well. So here you see those n equals 1, 2, and 3, different shells moving up, increasing energy as the electron moves from here to here to here. Okay? Okay, so the principal quantum number, or the n equals 1, 2, 3, 4, all the way to 7, is only one of 3 quantum numbers that we're going to describe here that is used to characterize the orbital of an atom. So how do we define orbital? It's a general region in an atom that an electron is most probable to reside. Remember that most of the space where an electron is empty space. It's empty space. So it's most probable to reside in that area is described. So when I draw this p orbital, all I'm saying is the probability of finding an electron within this region is most probable versus outside of that region. You won't find it, right? And with the p orbitals, since there's 3 of them, you kind of get another, for when you move up in the number of electrons that you have in the p orbitals, you get that second p orbital joining all the way up into the third p orbital. One is on the x, one is on the y, and the other one will be on the z plane. Kind of going, so one up, down, and then your third dimension back and forth, right? So that's the identity of finding the electron within these p orbitals. Whereas an s orbital, just spherical. So it kind of looks like, here's my sphere, and then you have the p orbitals that are coming up and down, in and out, and then this direction, back and forth, okay? And so that would be a total of 2, 4, 6, 8 electrons right there. That's a total of 8 electrons in those 4 orbitals. The s and 3p orbitals gives you a total of 8 electrons. And the thing about atoms is that's the most ideal number of electrons. And it's with those 8 orbitals when you're pairing with another one. Okay? So if one of these, each of these has 2 electrons in it, right? But if one of them only has 1 electron, oh, I'm not very happy about that. So I need to find a partner, and then you find a partner, you pair, and then you're creating a compound, or satisfying that vacancy somehow through chemical reactions. Okay, and that's where the chemistry is going to come into play. But this has to be the outside shell for that to take place. Okay, that has to be the most outside shell in order for that to occur. Okay, I'm actually going to pause it there